tools are way more fun than I am. I'd probably be using the tools too if I could, but you drop all your stuff. I'm going to talk today on voltage, current, and resistance. Chris, are we good there?
Yeah.
Okay. I'm going to talk today on voltage, current, and resistance, which is something you guys should all have been facing as you build your projects. We got voltage as what? If I asked you in one sentence to describe voltage, what would you say? Energy being put into a system. Okay. Good. Yeah, all the way back.
How steep the hill is?
How steep the hill is. It's a good analogy. Yeah, right here.
Oh, me?
Yeah.
It's what causes the electrons to flow through the circuit.
Yeah, that's my favorite one. What causes electrons to flow through the circuit. So you got to think of electrons as all they're doing is moving. The entire field of electrical engineering, all of it, everything around it is built to study how electricity flows and specifically how electrons flow through a system. We have this equation, voltage, V equals IR, voltage, current, and resistance, to describe what's going on when we can get the electrons to move and what laws dictate how those electrons move. So who could talk to me about current? No, let's do resistance first. Who can talk to me about resistance? It's a little easier. Yeah.
Limiting the current flow of the electrons through a system.
Right. So it limits the flow. Perfect. I love it. Anyone else have something they want to add? No? Nothing? Okay. That was good. I don't think I have anything to add. What about current? Who thinks they know current? Yeah, all the way back.
The rate at which electrons flow?
Oh, that's good. I don't think I need to be here anymore. You guys are set. So we have VIR, voltage, which is how high the hill is, or what was it that you said, Katie?
What causes the electrons to flow.
Yeah, what causes the electrons to flow. We have the resistance, what restricts the electron flow, and the current, which is the rate at which things flow. My favorite way to describe the relationship, or actually what happens with these electrons, is to personify the electrons. First, electrons are everywhere. They make up you, they make up the tables, they make up this. The quantum physics theories that we all currently ascribe to in the electrical engineering field say everything's got electrons. And the trick isn't in creating or destroying electrons, because you can't do that. The trick is convincing these electrons to move, to go from one place to the next. And we do that with voltage, otherwise known as motivation. So think right now, if you were all in this class electrons, and I'm the electrical engineer up here, and I say, okay, electrons, I want you right now to stand up, walk through this door, go out in the hallway, back through that door, and start doing laps around here. Raise your hand if you do it, just because I told you. Not because I'm the instructor, because I write the checks for these guys, but because if I was just some guy, I said, hey, I want you to do that lap. Who's going to do it? Nobody. Okay, good. What if I said, for every lap you do, I'll pay you $10? Who's going to do it? That's how much we pay our instructors. That's what we give them. They'd rather run laps for change. What about $1? Who's doing it for $1? I got 1, 2, 3, maybe half of you guys. I don't know what jobs you guys are working, but that lap for $1 is a deal. Okay. What about $100 a lap? Who's doing it? Everybody's doing it for $100. So if you're electrons, my bankroll, how many dollars or how much money I pay you to run that lap is the voltage. How much motivation is there? Some of you were willing to do it like the staff was willing to do it for $10. Some of you were willing to do it for $1, and some of you it's going to take $100 to get you out of that chair and walking around that lap. Okay, so now you know that's kind of voltage. If you want a few electrons to move, put a AA battery on it. You want a lot of electrons to move, you plug it into the wall. That's the difference. You're increasing the motivation for them to get up and move. Okay, yeah, question?
Would you say like the resistance is like the size of the door? It's like
Yeah, that would be a good thing, the size of the door, right?
the door was bigger.
But if I made the door the size of a baseball, I don't think any of you are going through that. But that's a good way to think of it. Resistance is essentially how big of a pain in the neck is it for you guys to do what I want you to do. So resistance would be, the analogy I like to use is if I said, all right, so now instead of this loop being here, now the loop is you have to go out here, go down that stairwell to the first floor, over to the other stairwell, up that stairwell, and then back through that door. Who's doing that for $1 per lap? We got one guy. Jabala likes to run. Kyle also likes to exercise. What about $100? Seriously, dude? $100 for 5 flights of stairs down and up? So that could be considered resistances. What am I asking you to do? If you as electrons sit there and you're like, I'm not doing 5 sets of stairs. I bet there's an amount of money that I could get you guys, every one of you, to stand up, run to the Hudson and back. It's probably a lot, but I bet you do it. Is that right? Okay, it's the same thing with electrons. If you ask an electron, say, okay, I want you to go through that LED. The electron's like, yeah, I'll do that with a AA battery's worth of motivation. But if you say to an electron, I want you to turn this motor, or run this garage door open, the electrons are like, it's going to take more than a AA battery. You got to plug it into the wall. You got to motivate me more. Okay, so that's resistance. What's going on? How much is happening? Who wants to guess what I'm going to say about current? Yeah.
How many people are in the room?
How many people are in the room? Well, here's the thing. If I said I want you to go to the Hudson and back for $1, the people in the room are exactly the same as if I said just do this quick loop, right? So that wouldn't describe the difference, yeah.
How fast they're running.
How fast they're running. Here's the thing. Electrons all move at the speed of light. But that is, yes, you're thinking the right way. But the rate at which the electrons travel is not what's going on, yeah.
So how much distance they can cover in a certain amount of time?
That'd be speed, right? Yeah?
How much work they have to do.
How much work they have to do, that's close. Yeah, one more.
How many electrons move?
How many electrons are moving, not just how many electrons are moving, but how many electrons are moving per unit of time. So if I sat here and I counted how many of you guys I got to walk through that door as part of the lab in a minute, that would be current. Let me make a little diagram. So if you had a battery here, and you wanted the battery to power an LED, put a resistor here. Okay, so battery, 1.5 volts, and this is an LED, and this is a resistor. You'll just have to take my word on some of that if you're not there when you start a project yet. But this is a circuit that's going to light up that LED. And voltage is right here, 1.5 amps. Resistance is set by this. And the current, what you have to do is you have to interrupt this, and you have to put an ammeter here. So you force all the electrons through your ammeter, and this ammeter is, the DMM can be an ammeter, you can set it to measure current. You sit there, all this does is it lets all the electrons pass through just like it was a wire, and it just counts how many are going. Not one by one, but it's got ways to count how much current is flowing through this. Are there any questions about this? Because I'm taking a leap here, yeah.
Could you measure the amount of voltage by measuring the amount of light coming out of the diode?
Can you measure the voltage by the amount of light coming?
Current.
Do you measure the current by the amount of light coming out of the diode? Yes, but only if you knew the ratio of light to current in the diode, and it's hard to get that number. So you could, in theory, if you already knew everything about the diode and you had a really nice light sensor, and you had this big setup, you could figure out the current through that based on the light. It wouldn't be a very accurate measurement. But it would be, you can at least tell if it's on or off or halfway on, right? It's a good indicator, yeah.
Would putting more LEDs act as a resistor?
Putting more LEDs? So like if I added one more here,
Sure.
yeah. Because now it's harder to go through 2 instead of 1. So now I would probably have these LEDs would be a little bit dimmer because the electrons have to do more work to go through the loop. So some of them aren't going to take the trip. So I'm going to be like, volt and a half, forget it. Not going. Sitting here. So we can get fewer electrons to go, which means less current, which means less light. Yeah?
And if you put it in parallel, not in series, would it be brighter or the same brightness?
So parallel like this. Where is this? Like that?
Yeah.
Okay, so what did I just do? Did I make it easier or harder for the electrons to run through that?
Easier. It's another door.
Easier, right? Yeah, there's another door. There's more places to go. There's a better path. Where there was only one path here, now there are 2. It's easier. So you get more LEDs flowing, so you get more light between the 2 of those. Now I'm not sure if they would if this wasn't here, this would light up more than if that was there. But the total light between the 2 of them would probably be more. Alright, these are all good questions. Anyone else have questions? Okay. So the relationship that we have between these things is called Ohm's law. I'm going to put this on the board and I'm going to put it really big because it's a big deal. If you want to get a job in electrical engineering, that's what you got to know. Half of what I do every day and get paid for is based on this, or at least a derivation of this. I don't know, how do you make a derivation of like 3 variable equation? There's ways. V equals IR. If you know that, you're doing pretty well, especially given that you're only in high school. So keep that in mind. Now, let's take the example of you guys. Do you conduct electricity?
Yes.
You say yes? You say yes? Who thinks no? One group. Alright. So you know not to stick your fingers into the outlet. Why?
Be a conductor.
Because you conduct electricity. But why is it that you don't have a problem picking up a AA battery? Yeah?
It's not that many electrons.
It's not that many electrons. Well, the number of electrons in here are constant, right? So if I was to put this in this LED circuit, if I was to take this battery and smack it in there, there would be the same number of electrons in here, right? So it's not a question of how many electrons are in here, yeah.
We have a high resistance, so to get any voltage, or to get any current, you need a lot of voltage.
We as people have a high resistance. So if you want anything, any current through here, you need a lot of voltage. That's exactly right. So let's calculate it out. If Robin's standing here, happy as can be. Look at him, he's a BlueStamp. Love him life. Robin likes BlueStamp. And we say, okay, Robin, can you hold on to these 2 wires for me? And I'm going to plug it into a battery. He's a trusting guy.
How would you pay me?
No, you don't get paid.
Is that because I signed your checks?
Yeah, exactly. Robin, hold these 2 wires for me. Do me a favor, hold these 2 wires. Alright, so we got 1.5 volts, right? And let's say, I mean these numbers vary from person to person, but Robin kind of likes salty food, so we'll say that he's got a resistance of 1 mega ohm. Right? So Robin is 1 mega ohm, which is equal to 1 million ohms. 1 million ohms. How much current is flowing through Robin right now? Anyone?
1.5 over 1 million amperes.
Yes. So this is 1.5, this is 1 million. So you can solve this equation, 1.5 over 1 million. 1 million ohms equals, I don't do math, but whatever that is, it's in amperes. I don't do math on the board because I always get it wrong. 1.5 over 1 million ohms.
Micro?
Yeah, I think it's micro. 1.5 microamps. Yeah, that's 1.5 microamps. Okay, so you go up to Robin. Say, hey, Robin. Thanks for holding on to those wires for me. Can you do me a favor and do it again? That's a wall outlet. Can you hold these wires for me real quick? Don't do this to him. You won't touch it after this. So now instead of that, we're at 120 volts. Right? He's lucky because it's the US. If it was Europe, it'd be 240. 120 over 1 million ohms. What do you think is going to happen? Not happy anymore. Not so happy. He doesn't like that. Let's do it. So we got 120 over 1 mega ohm. Who wants to do the math? Anyone? I'm not doing it, remember?
It's 1.2 times 10 to the negative 5.
1.2 times 10 to the negative 5. Is that right? Negative 3 saying? We gotta do it, somebody's gotta do it. Go all the way back.
Negative 4.
Negative 4, now I got 3 answers. Who wants to confirm one of them?
It's 3. Yeah, it's 4.
It's 4? 2 times 10 to the negative 4. Okay. So what is that? That's that'd be like 0.12 times 10 to the negative 3, which is 0.12 milliamps. That's 0.12 milliamps. So that's like, 100 times that. So 100, if you put 100 batteries there, you wouldn't want to touch them, for sure. But you also don't want to touch the outlet. So this is how you use vehicles IR to understand what the electrons are doing. That's the whole point. What are the electrons going to want to do? Is my resistor sized appropriately? Should I touch this? I don't want to touch that because it's over 40 volts. In general, anything over like 0.01 microamps is nothing you want anything to do with. There's such a small amount of current, right? Doesn't take much. Doesn't take much at all. You gotta keep that in mind when you're using vehicles IR. Any questions about any of that? If you can get this down pat, you can answer a lot of your own questions. Yeah?
How accurate is that formula, like in real life situations?
It's perfectly accurate.
Like 100%, like
100% accurate. Where you get inaccuracies is you didn't measure this voltage accurately, you didn't measure this current accurately. Like, if you're using this equation, if you don't know one and you have the other two, you're basing the other two on some measurement, right? And that's where your inaccuracy comes from. But this relationship is perfect. In theory, right? We can only test that to our ability to measure. So we may find as we develop more measurement technologies that this has some other turn here. The other thing that makes it weird is no resistor is perfectly resistive. There's also, and we're getting ahead of ourselves, but there's also inductance and there's also capacitance in every resistor. But they're so small that you can ignore them. In BlueStamp, I would just say a resistor is a resistor, and that's fine. Any other questions? No? That was a good one. How good is the equation? Usually equations aren't the things that are the problem. Usually it's the numbers you're putting into them. Kind of like a spreadsheet, a database. Anything else you guys have been wondering about with voltage, current, and resistance? It's such a neat topic. All engineers everywhere love it, yeah.
it's a little off topic, but in measuring resistance, when like you have like the length of the wire times the resistivity divided by the area of the wire. When you do that, does it matter like gravity at all? Like if you like put the electrons are going up compared to the electrons going down?
Oh, are electrons affected by gravity?
Yeah, basically.
You are getting like
Yeah. I thought
way
that
into
was
quantum physics. I don't know enough to answer that question. I could speculate on like, no, gravity is negligible in any appreciable current flow, but I couldn't point you to any references that would suggest it. But especially BlueStamp, definitely negligible. Do not worry. Don't think that you can get your project to work because you flip it upside down so the electrons can flow better one way. Don't think that. Electrons do what electrons do. I saw a hand. Anyone? Somebody backed out? All right. Anything else you guys are wondering? Electron flow is happening in all your starter projects. Okay? And that's that. I'll let you get back to the fun tools and building stuff. Yay!